So basically, the principle of superposition in geology is the older you go, the deeper it is. So think about something that deposits on the ground. If something's forming, it'll be the first layers on the bottom that form first, and then subsequent layers that come on after that. So it's a relative dating method. It's not absolute. Being that it can't be absolute because sometimes these layers fold up like this, and then say this layer, say it cuts right there from a fault, it'll split like that. So this layer will move up, and this layer will move down, and this layer will be right next to this. So they'll look to be the same age, but they're not, because you have to realize the fault happened. So that's principle of superposition. The deeper you go, the oldest the material is. That being said, with DH ratios, it's backwards. The principle of superposition. Okay, let's not do that. Let's do this one first. Okay, so you have a very young hot star here. The whole body is 1 deuterium per 10 million hydrogens. As it cools to the next stage and shrinks and loses mass and loses the lighter hydrogen to interstellar space, the whole body becomes 1 deuterium to a million hydrogen. But what happens is because the star was forming the interior object, now this isn't perfectly representative. This is just an idealization. So obviously this is going to be iron and nickel in the center, but we're going to assume that it's going to be hydrogen and deuterium. The hydrogen and deuterium that make molecules like water and acetylene and hydrocarbons and all that stuff, the ratios that will be composed of will be the lowest ratios, the 1D over 10 million H that were present in the young star body. So that will be here, and then as the star continues to lose mass, the ratio decreases for the whole body. And then it continues doing that same pattern. You'll have 1 to 10 million in the center, 1 out of a million right in the right outer layers of the core, and then you have the atmosphere being 1 over 100,000. And this is a much more evolved star, so the ratio drops when the star evolves, as the whole body evolves. And the oldest material will be in the center with that high ratio right there, as the younger star. And then when it continues cooling and collapsing, then the ratios get really interesting, because then more and more layers of this ratio are deposited in the center. So you have the very center as the lowest ratio, then it rises up and rises up, and then the very outer regions, the ratio is 1 out of 10,000 on the outer regions. So what you have here is, if you look at the deuterium hydrogen ratios, it'll be backwards. For our sake, this is an absolute method. So you have the youngest material in the very center, and as you move out from the center of the star, the material, the deuterium hydrogen, gets older and older and older. This is why when you take DH ratios of highly evolved stars, you should expect this ratio to decrease as you move towards the interior regions of the ancient dead star. On the other hand, if we are to use the principle of superposition and try to make the DH ratios work for that, it would be strange, because if you have the really old material in there, that wouldn't make any sense, because then that would mean the star started off as extremely old and wouldn't have the very low ratios in the beginning. So this isn't correct with the DH, meaning the material that looks the youngest is actually the oldest material, so it goes backwards. So you have a very young material starting out, going older as you move up, and then the relative method going down. So they crisscross. They go backwards from each other. There's an absolute method, and then there's a relative method, the principle of superposition. And this is most likely for physical material when it deposits. But this is when the material combines into molecules, because that's what hydrogen and deuterium do. They combine into heavier and heavier molecules. So you have oxygen, and this could be deuterium, and this could be hydrogen. So that's heavy water right there. And then I think acetylene is a carbon, and then hydrogen, and a hydrogen over here. But then heavy acetylene would be, a deuterium, carbon, and these three lines right here is a triple bond, and you have maybe a hydrogen over here. So you could have a deuterium, carbon, triple bonded carbon, and a hydrogen, or both of these could be deuterium. That'd be an extra heavy acetylene. Or like methane. So you have four hydrogens, or three hydrogens, and maybe a deuterium right here. So basically, the deuterated material is going to be more present in the more evolved stars, because they've had enough time to get rid of the undeuteriated material. And the lower the deuterium, the more center to the star you're looking at. And you can tell when it formed by its deuterium ratio. So say, for instance, you take a sample of a star and you see, the deuterium is 1 out of 10,000. Now, if you measure that in the top of the star, yes, that's the outer atmosphere. But say you take a star that has an outer atmosphere of a ratio of 1D to 10,000 H, and you go and you find, oh my goodness, where is this 1 out of 100,000 coming from? That's anomalous. Well, clearly, it's not anomalous. What you did is you measured a very, very, very deep interior that for some reason had an upwelling of material coming out from the interior of the star, which could be caused by multiple things. And the reason why I want to mention that is because that should be, when we get really advanced telescopes coming out, and say you have a brown dwarf that, has, say, like 1 out of a million. Oh, crap. Yeah, there we go. 1 out of a million DH ratio in the very center. And then we measure its outer atmosphere as being 1 out of 10,000. And all of a sudden a flare happens. So boom, all this material comes blasting out, and it's 1 out of a million of a ratio of material. Then we know how far the material came from in the central regions, or if the flare was just a surface phenomenon versus an interior phenomenon. And that's really advanced stuff that doesn't exist yet in astronomy, because they don't even realize that you can take a star's deuterium hydrogen ratio and give it an age. And for those who don't already know this, the youngest stars have very, very low DH ratios. And then as the star ages, forget this, This is 19th, 20th century stuff we can ignore. As the star ages, it goes to lower DH ratios. All right. If anybody has any questions, just let me know.